Jai Hind everyone, my name is Nandita Goyal and I am working as an assistant professor in Department of Information Technology at AKGEC Ghaziabad. So today I will be covering the topic CPU scheduling algorithms, which is a part of operating system subject. So the contents that I will be covering today include different CPU scheduling concepts, then the performance criteria which are required to evaluate the different scheduling algorithms. Then we will be discussing the different types of CPU scheduling algorithms which are available and which are divided into two categories. One is non-preemptive algorithms and the other one is known as preemptive algorithms. So today in detail we will be discussing the various non-preemptive algorithms, that is first come first serve algorithm, which is commonly known as FCFS, then shortest job first algorithm, which is known as SJF, and then finally we will be discussing priority based non-preemptive scheduling algorithm. In my consecutive lectures, I will be discussing about the preemptive scheduling algorithms, which include round robin, shortest remaining time first, and even priority scheduling, which is a preemptive version. The basic concepts that will be covered in this lecture include that how we can maximize the CPU utilization, which is actually obtained from the concept of multi-programming. Then we will be discussing about the CPU and IO burst cycles which are required for the execution of a process. And then finally, we will be discussing about the CPU burst distribution and the various scheduling algorithms which are related to it. Now, if I talk about that how a CPU gets the request and how it actually executes the request from a process. So what happens whenever a process is ready for its execution, it is being decided by the scheduler that which process is to be given to the CPU for execution. Once the process has been selected by the scheduler, the entire information about the process is being stored, that is, we'll add the information about that particular process and then we'll load that process to the CPU. So this is known as when the process starts the execution with CPU, this is actually known as CPU burst, when the process is actually executing with CPU. Now whenever we talk about a process, it always happens that a process requires both the CPU burst as well as the IO burst. So for some time when the process has executed with the CPU, it happens that it needs to go for some input output requests. So that is shown by this wait for IO. Now when the process is actually waiting for IO, this is known as IO burst. So first there has been some CPU burst, that is the process is being given to the CPU for execution. In between when it was executing, it required certain IO for which it goes for the IO burst. Now what happens when it goes for this IO request, the CPU is idle. So instead of keeping that CPU idle for that time, what we can do, we can assign any other process which is in the ready state to the CPU. This will actually maximize the CPU utilization because we are keeping the CPU idle for the minimum amount of time. So here again we will bring another process which is in the ready queue, then we will store its information and then it will start the CPU burst. Now again it might happen that the process which is being executed by the CPU, it might require certain IO, so it will go for the IO burst. Meanwhile, either the previous process which has gone for IO might have come back in the ready queue, so the scheduler might have selected that particular process or any other process from the ready queue. So this alternate CPU burst and IO burst keeps on going, and this is how actually the CPU utilization is maximized, because now the CPU will remain idle for the minimum amount of time. So this is what we were talking about as the first concept, that is the main aim here is to maximize the CPU utilization by scheduling some of the processes from the ready queue to the CPU. Now CPU scheduler, as I have been using the term scheduler, so now what is this CPU scheduler? When we have a number of processes which are in the ready state and which are in the main memory, now it is to be decided that which process should be executed first. So this decision is being made by CPU scheduler. So it selects from among the different processes that are in the memory and are ready to execute and allocates CPU to any one of them. So now the CPU scheduling decision may take place whenever there are certain situations, like there is a process which was running, that is, it was being executed by the CPU and it has to go for some IO, and that means it basically moves from the running state to the waiting state. So in this case, when a process moves from the running to the waiting state, some other process needs to be brought to the CPU. So that means here a CPU scheduling decision will take place. Now another scenario can be when a process switches from running to ready state. This usually happens in a preemptive scheduling scenario, that is when a process is executing, but suppose a higher priority process comes into the ready queue, then that higher priority queue has to be assigned the CPU. So whatever process was running with the CPU, that has to be removed from the CPU and it will be brought to the ready state, because it is not waiting for anything, it is ready, but due to the higher priority process, it has to move from the CPU. So in this case, the process will be moved from the running state to the ready state, and a higher priority process will be brought from the ready state to the running state. So again, this decision will be taken by the scheduler. The third scenario, when a process switches from waiting to ready state. Now any process which moved for certain IO request or was in waiting state due to any of the requests, it might be now again ready to get the CPU. So it will move from waiting to ready state. Now as soon as it comes to the ready state, since it is in the ready queue, at some point of time the scheduler will again assign this process to the CPU so that it comes from the ready to the running state. So here again the CPU scheduling decision will take place. And the last case where a CPU scheduling is required, when a process has completed its execution, that is whatever CPU and IO burst time it required, it has already completed with its execution and now it is terminating, that is moving to the termination state. Now the CPU will become idle, so obviously some process from the ready queue will be brought to the CPU. So again here CPU scheduling decision will be taken. So these were the 4 scenarios where a CPU scheduling decision may take place. Now when we talk about scheduling, there are certain criteria through which we can analyze any scheduling algorithm or any scheduling scenario. Like first one is known as CPU utilization. That is always the aim of the system is to have maximum CPU utilization, that is keep the CPU as busy as possible. So this is actually known as CPU utilization. Then we have a next parameter which is known as throughput. So throughput is the total number of processes which have completed their execution per unit of time. So whatever is the number of those processes, that is known as the throughput of the system. So we can say that the greater the throughput of the system, the better will be the performance of the system. Then we have another term which is associated with the performance, that is known as turnaround time. So this turnaround time is actually the total amount of time which is used to execute a particular process. Then we have something known as waiting time. It is actually the total amount of time which is being spent by a process waiting in the ready queue, when it is ready to execute but it has to wait because it is not being scheduled or it is not being provided the CPU execution time. Then we have the last parameter known as the response time. This is actually the amount of time which a process takes when it has been submitted to the ready queue and when it first gets the response. So this is known as the response time. It is not actually the final output, we are not talking about it, but when a process has entered the ready queue and the first time it will get the CPU execution time, so that time is known as the response time. Now we have, whenever we are talking about scheduling, we have this term context switch, and this is a very important term in terms of CPU scheduling. We can say, now what is context switch? See, we are talking about multi-programming, that is, we are having multiple processes which are in the ready queue, and from the ready queue they are being brought to the CPU. So whenever this switching is done, that one process is there with the CPU and another is being brought from the ready queue to the CPU, and the first one is moved out. So this particular thing is known as context switching. And what is actually done in context switching? We have something known as PCB, which we have already talked about in the previous lectures. So this PCB or process control block actually stores the state of the process that is being executed by the CPU. So whenever a new process is brought in, so this information is to be overwritten. So this is known as saving the context switch information, and the process of bringing the new process and removing the old process from the CPU is actually known as context switch. So whenever a CPU switches to any other process, the system must save the state of the old process where it has stopped the execution and load the saved state of the new process, which whatever was its state, it is being reloaded to the system. So this context switch time is actually a overhead because we are not providing any execution during this time. So the system is not actually doing any useful work, but still it is a very important part for CPU scheduling and has to be done. And the time which is required for context switching actually depends upon the hardware support. So if we have the system has proper hardware support, so we can even reduce this context switch time. So this diagram is actually showing how this context switch is done from one process to another. So this is actually first process which is being denoted by P0, and we have a second process which is being denoted by P1. This is the operating system handling how the context switch will take place. So first the process P0 was executing. Now due to some requirement, it has to move from the CPU. So what is to be first done? An interrupt or a system call will be made that will ensure that the state of this process is being saved into the PCB of this particular process. And then once this has been done, saving of state has been done, then it means that now some new process is to be loaded into the CPU. So we'll reload the state for this process 1, and once the state has been reloaded, only after that this execution of process P1 will start. Now suppose this process again wants to wait for some IO. So what will happen? Its state will be saved into its PCB, and then we can reload the other process. Suppose we are again reloading P0. So now after this reloading is done, the process P0 will again starts the execution. So we can clearly see now here it was executing, P0 was executing, then it wanted to make a switch. So its state was saved and the state of P1 was reloaded from its PCB. Then it started executing. When it wanted to move from the CPU, again its state was saved and the state of the previous process was reloaded and it started the execution. So this is how the context switching actually happens. Now coming to the CPU scheduling algorithms, the CPU scheduling algorithms have been divided into two categories. So first one is known as non-preemptive scheduling. Now what do we mean by non-preemptive scheduling? It is actually when this type of scheduling is used when a process terminates or process switches from the running to waiting state. That is, a process will move from running to waiting state only when the process terminates. The system is not going to forcefully remove the process from the system due to any of the scenarios. So once a process gets the CPU time, it will complete its execution time, and the operating system is not going to forcefully remove that process from the CPU. So in this type of scheduling, once the resources are allocated to the process will keep holding the CPU till it gets terminated and reaches or itself reaches a waiting state. So the examples of this type of scheduling include FCFS, that is first come first serve algorithm. Then we have shortest job first algorithm, which is known as SJF, and we have even a priority based algorithm in a non-preemptive mode. This priority based algorithm can execute in both ways. It can be preemptive as well as non-preemptive, but here we are going to look at it in the non-preemptive mode. Now, if we talk about preemptive CPU scheduling algorithms, the preemptive CPU scheduling algorithms, once a process has been given to the CPU, it might happen that after some amount of time it is being removed and some new process is being scheduled. The reasons for this might be that a higher priority process has come into existence in the ready queue, or it might happen that we are using a round robin execution fashion, that is we have decided some time quanta like 2 units of time. So every process will execute for 2 units of time, and then after getting its turn it will again move to the ready queue. Or we can even have shortest remaining time first algorithm, that is we select the process for CPU which is having the minimum amount of CPU time requirement. So these can be the reasons for having a preemptive scheduling algorithm. Now coming to the first come first serve algorithm, as the name says, here we will be maintaining a queue, and whichever process arrives in the ready queue first will be getting the CPU execution turn first. So it means that a resource cannot be withdrawn from the process before the process has actually finished its running or finished its execution, or a process has come to its waiting state. So till then we cannot remove the resources. The mode of this algorithm for running is non-preemptive, and the criteria for which we will be doing the scheduling is arrival time. That is, whichever process will arrive first will be scheduled first. So let's look at one of the examples. We have 6 processes in total, that is P1, P2, P3, P4 and P4, P5 and P6. Now in this second column we are given the arrival times for the process, that is the process P1 has arrived at time 0, P2 has arrived at time 1, even P3 has arrived at 1, P4 has arrived at 1, P5, 2, P6, 3. Here we are not looking at the units of the time, we are considering that all the processes have the same units for arrival time as well as burst time. Okay, then we have burst time. Burst time is the total CPU burst requirement for the process. So P1 requires 9 units of time, P2 requires 3 units of time, P3 requires 2 units of time, P4 requires 4 units, P5 3 units and P6 2 units. Now first of all, what we'll do to check that how these processes will be scheduled, we'll draw something which is known as Gantt chart. So to draw the Gantt chart, what we do, we just represent the arrival times and the completion times of each of the processes with the help of a diagram. So first of all, if I see, I have my ready queue. Okay. So now in this ready queue at time 0, we'll have only a single process because the arrival time of only one process is this 0. Rest of the processes have arrived at 1, 2 or 3. So at time 0, we'll have only a single process in the ready queue, that is P1. So what we'll have to do, we'll have to schedule the process which has entered the ready queue first, that is P1 has entered the ready queue first. So we'll have to schedule P1 first. After this, so now what will happen, we'll draw the Gantt chart. At time 0, this P1 process will get the CPU execution, and since it is a non-preemptive mode, so whatever CPU burst it requires, it will complete its execution. So the time requirement for it is 9. So that is, the P1 will complete its execution at time unit 9. By the time P1 completes its execution, all the other processes have also arrived in the ready queue because P2 has arrived at 1, P3 has arrived at 1, P4 has arrived at 1, P5 2 and P6 3. So up to 9, all the processes have arrived and the order of arrival is P2, P3, P4. Although all these processes have arrived at time 1, but we can consider any of them to have arrived first because the time is same, but we'll keep it as per the process IDs, that the process with the smaller ID, I am considering it as first and with the greater ones later on. Okay, so this order can even be changed. You can consider it as P3, P2, P4 or P4, P3, P2. That is not going to make any difference in the overall completion time. Okay, so this can be done. Now, after this, P5 has arrived at time 2 and then P6 has arrived at time 3. So, this is the order in which they have arrived. Now, P1 has already completed its execution. Now, after this, P2 will be given the CPU. So, P2 requires a total burst time of 3 units. So, obviously, it will take 3 units and will complete at 12. 9 plus 3, it will complete its execution at 12. After this, P3 will be assigned the CPU. It requires 2 units of time. So, it will complete its execution at 14. After that, P4 will be assigned. And P4 requires a total of 4 units of time. So, it will complete its execution at 18. Then P5 requires 3 units of time. So, it will complete its execution at 21. And then P6 requires 2 units of time. It will complete its execution at 23. Okay, so now let's see that what are the completion times of each of the process. So, process P1 will complete its execution at 9, P2 will complete its execution at 12, P3 will complete its execution at 14, then P4 will complete its execution at 18, then P5 at 21 and P6 at 23. So, this way I have calculated the completion times for each of the processes. First, I have drawn the ready queue. I have seen that how the processes have entered into the ready queue. Then, applying the first come first serve criteria, I have drawn this Gantt chart, and from this Gantt chart, I have finally calculated my completion time for every process. Now, coming to the another parameter, that is turnaround time. So, I have to calculate the turnaround time. So, this is the standard formula to calculate the turnaround time, that is whatever is the completion time of each process minus its arrival time. This is the total amount of time that is required by the process to complete its execution. Okay. So, now using this formula, we will calculate the turnaround time for each of the process. So, for process P1, we will have 9 minus 0, that is the turnaround time is 9. Then P2, 12 minus 1, that is 11. Then 14 minus 1, that is 13. Then 18 minus 1 is 17. Okay. Then 21 minus 2, 19. And 23 minus 3, that is 20. Okay. So, these are my turnaround times. Now, I have to calculate the waiting time for each process. So, waiting time is turnaround time minus the burst time. I already have the turnaround time for each of the process. I just have to deduct the burst time from it. So, the waiting time for process P1 becomes 9 minus 9, that is 0. And see, the process P1 did not wait for any other process to complete its execution. So, this is correct. Now, for process P2, it is 11 minus 3. So, it becomes 8. Then, for next process 13 minus 2, it becomes 11. 17 minus 4, 13. 19 minus 3, 16. and 20 minus 2 is 18. So these are my waiting times. Now what I can do, if anybody asks me that what is the average turnaround time and average waiting time for this system, so how I am going to calculate this? Average turnaround time is nothing but just add the turnaround times of each of the process, that is 9 plus 11 plus 13 plus 17 plus 19 plus 20, and then we'll divide it by the number of the process, that is 6. Same way we can calculate the average waiting time. We'll just add up all the waiting times and then we'll divide it by the number of process. In this case it is 6. So this way we can calculate the average waiting time of the system. So this was my first come first serve algorithm. These formulas will remain same for all the algorithms. The only thing which will differ is that how we schedule the processes. So in first come first serve, the mode of working was non-preemptive and the scheduling criteria was arrival time. Now coming to the advantages of FCFS. FCFS is a very straightforward algorithm and it is easy to implement as it can be simply implemented using a queue. Then in FCFS there is no chance of starving of any process because the process which has arrived in the ready queue is going to get its turn as per its arrival. So no process is going to starve. Then there is no consideration of process priority, that is all the processes have equal rights, or we can say that every process is equitable. But if I talk about the disadvantages of FCFS, it usually has in terms of performance long waiting time. Then there is another problem which is there in the FCFS algorithm, which is known as Convoy Effect. I'll explain the concept of Convoy Effect with an example. So let's take this example and this will make clear that what exactly it means. See, suppose I have two processes P1 and P2. The arrival time for P1 is 0 and the arrival time for P2 is 1. But if I look at the burst time requirements, P1 requires 100 units of CPU time and P2 requires 2 units of CPU time. Now since P1 has arrived in the ready queue first, P1 is going to execute. Now what will happen? If we'll execute P1 first, as per the algorithm, it will require 100 units and here P1 will complete its execution. Once P1 has completed its execution, P2 will get the CPU time and it will complete its execution after 2 units of time, that is at 102. Now if I look at the waiting time of P2, so P2 was a small process requiring a very small CPU burst time, but it had to wait for almost 98 units of time to get its turn. Okay, now if this scenario was, so this is going to increase the overall waiting time of the system. Now if it was the other way, that is the process P2 had arrived first at time 0 and P1 has arrived at 1, and again the burst times are same, that is P2 requires 2 units of time and P1 requires 100 units of time. So now if I draw this Gantt chart, at 0 P2 would have got the turn, completed at 2, then P1 completed at 102. But now just see the waiting time for process P2 is 0 and for process P1 is 2 units of time. So here the overall waiting time is 2 units and here the overall waiting time was 98 units. So we can see that how the performance has been degraded if a larger burst requirement process enters the ready queue first. So this is the problem with first come first serve algorithm, that we are not using any preemption. So if a longer process which requires too much time at CPU enters the ready queue first, then it will actually degrade the overall performance of the system. So this effect is known as Convoy Effect, and this FCFS algorithm actually suffers from this Convoy Effect. Now coming to the next scheduling algorithm, that is known as shortest job first. So as the name says here, what scheduling criteria will be applying? The processes with smaller CPU burst requirements will be given the CPU first, and the processes which require larger CPU bursts will be given the CPU later on. So the mode of working will again be non-preemptive, because we'll be once a process has been assigned the CPU, we are not going to remove it in between until it completes its execution or it itself goes to the waiting state. So it is actually a optimal algorithm which gives minimum average waiting time for a set of processes. So the mode of execution here again it will be non-preemptive, but the scheduling criteria here is going to be the burst time. So let's take a look at the example and see how it works. So this is a non-preemptive shortest job first algorithm. Here we have 4 processes P1, P2, P3 and P4. The arrival times for these processes are given as 0, 2, 4 and 5, and the burst time is 7, 4, 1 and 4. Now let's draw the residue first. See, if I draw the residue at time 0, which process I am going to have in my residue? I have only one process, that is P1. So now since I have only one process, so whatever its burst time, I'll have to assign the CPU to it, because I cannot compare the burst time of this process with any other process because there is no process in the residue. So first I'll have to start the execution of P1. I don't have any other choice. So here I have assigned P1 at time 0 to the CPU. Now since its burst time requirement is 7 and I am working with a non-preemptive scheduling algorithm, I'll complete the execution of P1. I cannot remove it in between. So it has completed its execution at 7. But when the process was executing by the time 7, what all other processes have arrived in the system? P2 has arrived, okay, P3 has arrived and even P4 has arrived. Okay, because I completed the execution at 7 and the arrival times are maximum up to 5. Now, if I look at the burst times of all these processes, this is already executed. It requires 4 units. It requires 1 unit. It again requires 4 units. So, which one is the smallest out of these 3? Obviously, P3. So, now I am going to assign P3 to the CPU. So, this is, I have assigned P3 to CPU and it requires 1 unit of time. So, it has completed its execution at 8. So, now even P3 has completed its execution. Now, coming to P2 and P4, since both of them require 4 units of time, I can assign any of them to the CPU, but here I am trying to use smaller IDs. So, I am assigning P2 to the CPU first and then I will assign P4. Even you can reverse it. It is not going to make any difference. So, now P2 is being assigned. It requires 4 units of time. So, it will complete its execution till 12 and then P4 will be assigned. It again requires 4 units of time. So, it will complete its execution at 60. So, now the same way, applying the same formula, we can calculate the total completion time. So, if I talk about the completion time for my process P1 is going to be 7. Then for process P2 is going to be 8. Process P3 is going to be 12 and process P4 is going to be 16. So, these are my completion times for each process. Even if I want to calculate the turnaround time and waiting time, I can calculate this. Okay, turnaround time is going to be my completion time minus arrival time and waiting time is going to be turnaround time minus burst time. Okay, so this can be calculated using this. So, same way I have calculated it and the average waiting time comes out to be 4. So, this is how we can apply non-preemptive shortest job first algorithm. Now, coming to non-preemptive priority scheduling. Now, here what happens is that we have assigned an additional parameter with each of the process, that is known as the priority. So, now each process has a priority number associated with it. Okay, so depending upon the priority, we are going to assign the process. So, scheduling criteria here will become priority and the mode which we will be discussing just now is a non-preemptive version. Although we have a preemptive version for priority scheduling as well, but right now I'll be discussing only non-preemptive one. So the processes are scheduled according to the priority number assigned to them. Once the process is scheduled, since it is a non-preemptive version, it will run till the completion. Okay, so but if I talk about the problem over here, the problem is starvation. That is, the processes with low priority sometimes never even get the execution. So this is the major problem with this algorithm, and we have a solution to this problem which is known as aging. In aging, what happens with time? We increase the priority of the process. If a process has been waiting for a very long time, we keep on increasing its priority so that sometime it will obviously get the execution time. So this solution is known as aging. Now let's look at the example of a non-preemptive priority scheduling. So here we have the different priorities associated with the process. We have 7 processes in total. We have the arrival times and we have the burst times. So we are considering that the smaller number means higher priority. So that means the priority 2 is the highest one and the priority 10 is the lowest one. So if I am going to draw the Gantt chart basis on the basis of the ready queue, so what happens at time 0? I have only one process, that is P1. So I execute P1 till its completion at 3. Till time 3, I get 2 other processes, that is P2 and P3. If I consider the priority of these, P3 is having the higher priority, that is 3. So I'll first execute P3. It requires 4 units of time, so it will complete at 7. Then till 7 arrival time, I have all the other processes which have arrived in the ready queue. So on the basis of priority, after 3 I am going to execute the process P6, which is having the priority 4. Then after this I am going to execute the process P4, which is having the priority 5, and then P2, P5 and P7. So this is the Gantt chart which is being drawn for this particular example. From this Gantt chart, I know the completion time of P1 is 3, P3 is 7, P6 is 11, P4 is 13, P2 is 18 and so on. So I can calculate the completion times, and from the completion time I can easily calculate the turnaround time and my waiting time using the formulas. So this is how this algorithm works. Thank you.